research projects, including silica glass DVDs on the Mars exploration rover and Phoenix lander carrying millions of names and Mars literature, the life biology experiment that flew on the Russian Phobos sample return mission, and he led a NASA grant studying microrovers assisting human exploration. He's the program manager for the Planetary Society's LightSail solar sail mission, for Planetary Society's LightSail solar sail missions. He has also overseen or managed a number of additional projects designed to excite and involve the public in space exploration. And I want to say, Dr. Betts, that LightSail is one of those projects that really has excited the public. And for some reason, it has struck a chord for its elegance and beauty, I suppose. So we're very excited to have you here. Thank you so much for the Planetary Society for visiting Izmir. And at this point, I'm gonna give you the time, ladies and gentlemen, Dr. Bruce Betts.
Hello, everyone. I hope your workshop is going well today. And I'm very excited to talk to you all about LightSail and solar sail. My dogs are excited, so you may hear them bark occasionally because they love solar sailing. And it's funny that way. And we'll get going. I'll go ahead and share my screen. Try to push the right buttons. Okay, that should look right. Hopefully you're seeing a title slide. So the Planetary Society is the world's largest space interest group. We're international. We have tens of thousands of members. We're not for profit. And the LightSail mission was not only the first small solar sail mission with a small spacecraft, but also completely funded by individuals from around the world in terms of how it was supported and funded. All right, so I'm going to give you a little background on solar sailing. So I know we've got a diverse group that may be familiar with it or may not. And then we'll talk about projects that led to LightSail 2. And then I'll talk about the LightSail 2 mission, which is currently in orbit, trying to do that solar sailing thing. So amazingly, Johannes Kepler, in a letter to Galileo, of all people, in 1608, basically after observing comets and the way the tails moved outwards from the sun, had this quote: "Provide ships or sails adapted to the heavenly breezes, and there will be some who will brave even that void." And he did have more discussion, obviously not all right, but he had the concept that there was something pushing out the comet tails, and maybe one could harness that. So basic propulsion, or basics of solar sail propulsion: light carries energy and momentum that can be transferred with photons. Light is pushing on me and pushing on you right now, just a little teeny tiny bit. And so it's irrelevant in our normal everyday life. But in space, in the vacuum or near vacuum of space, if you have a big shiny sail and a relatively low mass spacecraft, then it actually matters. And it's still a small push, but it's a constant push. And we'll talk about that a little bit more. A misnomer, an unfortunate terminology, at least in English, of the solar wind. Solar sailing does not use the solar wind, which is charged particles coming out from the sun. Solar sailing uses the more roughly more than 10 times more powerful push of solar photons, of light coming out from the sun. So we use solar radiation pressure. This is the push of the light from the sun to propel the spacecraft. That's the concept. Current design uses aluminized film. For example, we use aluminized mylar, same thing that may be in birthday balloons. Polyimides are popular and being used on some of the future solar sail missions. And if you will get a push from the photons even if you don't have a shiny object. And in fact, it affects the orbits of spacecraft, particularly going towards the sun. And so a messenger from Mercury actually used solar solar radiation pressure to tweak its orbit a little bit because of the push. But if you can unfurl a big area, and if you make it shiny and reflective, if you had a perfect reflector, you double the momentum as the photons hit and bounce back or bounce off. So this is my least way I phrase what I consider rule number one of solar sailing. The acceleration of a solar sail spacecraft is proportional to the area of your sail divided by the mass of the whole spacecraft. So what this means, and perhaps it's kind of obvious, but if you make a bigger sail, you get a bigger push. If you make a lower mass spacecraft, you effectively get a higher acceleration. So what ideally you would want is big sails, little mass spacecraft. So why do we even care about this? Why do solar sailing? We've got chemical propulsion out there. We've got other methods of propulsion. Well, first of all, there's no fuel required. Like a sailboat, you don't need to have fuel because you've got sunlight, or maybe in the future, high-powered lasers. Excuse me. You get a small push, but it's a constant push. So the push on the LightSail spacecraft is about the same as the weight of a housefly on your hand on Earth. It's very tiny, but it's always there if you're in the sunlight. And so you can keep accelerating and either increase your speed, or you can do creative orbits, non-Keplerian orbits, where you can do station keeping. So for example, right now we have spacecraft at Sun Earth Lagrange point 1, about 1 million gravitational balance point, about 1.5 million kilometers between the Earth and the Sun. Those spacecraft will stay there as we orbit the sun, and they give warning about solar storms and the like before they hit Earth. Well, it's not stable in terms of being on the Earth-Sun line to put a spacecraft farther inwards, because it will be going faster and it will move out of the Earth-Sun line. But if you have a solar sail and you orient it right, you can balance the forces so that you can be inwards of L1 and still have stay on the Earth-Sun line, and thus give more warning of particles, charged particle storms coming from the sun. Theoretically, you can also use it for pole setting and having it over the pole, say, of the Earth for constant observation of the poles, which is not possible without a balanced force. And then you have a lot of flexibility, not requiring fuel, so you can do multiple rendezvous, say, with multiple different asteroids. You can also get a very high speed going away from the sun, in theory, particularly if you go in towards the sun and then use the sunlight to push you far out and rapidly away from the sun. So it's not, solar sailing is not the answer to every question of how do you want to get somewhere in the solar system. And it gets ineffective, for example, out past, say, Jupiter, because of the light pressure being much lower. But there are a lot of things that it can do, and it's in this early phase and exciting phase of demonstrating and learning how to use it. So the Planetary Society tried to fly the world's first solar sail ever to use solar pressure to push on the spacecraft, and that was Cosmos 1, was launched in 2005. It landed in the ocean in 2005, shortly after it was launched. In the nature of the space game, there was a launch failure, and that ended that hope. The actual first solar sail mission was flown by the Japanese Space Agency, JAXA. It's called Icaros, and it was deployed on the way, it was dropped off from the Akatsuki spacecraft on its way to Venus, and so on an interplanetary trajectory. It had free-flying cameras, which was neat, a little camera that they deployed outwards that captured this image in a little sequence of deployment. Had a very origami inspired folding of the sail, and they spun it and it came outwards due to the spinning nature of things. So very creative. Was 196 square meters and 307 kilograms in mass. Notice that's a pretty high mass, and it's not intuitively obvious, but if you do the calculations, you get very little acceleration from an area to mass ratio like this. But congratulations, they demonstrated the first thing. They also were not able to turn very rapidly with and control things with their control system. So meanwhile, the Planetary Society is still loving the concept of solar sailing. It's like, what do we do? What do we do now, if anything? And it was during this period that the CubeSat field developed. So these small standardized spacecraft based on 1U or 1 unit cubes, 10 centimeters on a side. And they became very popular, as you're probably aware, many of you, with Earth, for Earth orbit applications, particularly for universities. Interestingly, more recently, they've been picked up a lot in space agency use and larger company uses. But they're great for Earth orbit, but they don't have much room to stick fuel on them. So they lack a flexible interplanetary propulsion method. If you wanted to send a CubeSat outwards, yeah, you can do it with your launch, but you can't make many adjustments along the way. NASA did a demonstration of NanoSail, which had a launch failure, and then NanoSail D2, which was a 10 square meter, 4 kilogram spacecraft designed purely to deploy and didn't have anything to do solar sailing, was effectively a drag sail, which is another application of anything shaped like a sail that you can use to drag yourself out of orbit. That's being looked into for orbital debris type applications. And they successfully got NanoSail D2 after a delay in the deployment that got it deployed and had a fairly simple, effectively spring-loaded deployment. And then as the drag increased in the lower atmosphere, they were pulled down as a drag sail would. And but they didn't have any of the avionics, any of the design to do solar sailing per se. So Planetary Society saw a new direction to take, which was, hey, can we demonstrate that you can use solar sailing with these small spacecraft that could really use a propulsion technique that's more than what you can carry on a very, very tiny spacecraft. Thus was born the LightSail program. And this was the concept art for deploying a sail with a small 3U CubeSat. So 3 of these 10 centimeter cubes in terms of size stacked together. And here are our program goals: demonstrate controlled CubeSat solar sail propulsion, raise the public and technical profile of solar sailing. One, we're all about the public and getting the public involved in space exploration, engaged with it, but also just to raise the profile of solar sailing within the technical community. And then, of course, excite and engage the public, which, as you've said, that we've had some nice success with, and then share our results. So we've done technical publications, we do things like this with our members to let them know what's going on with the mission, and we will continue to do that and analyze and share whatever we've learned. So as I mentioned, we're an independent international nonprofit, and this LightSail program has been funded entirely by individual donors, over 50,000 of them. And here's an example, the classic bread with a spacecraft picture. Well, actually, it's not very classic, but I like it because it really shows the size of our spacecraft. This is our engineering model, so lacks a lot of the guts to the spacecraft, a lot of the inside electronics and sail and everything else, but it's the same exact size. And it's not as tasty as bread, but my dog said, did you say bread? Are we getting bread? No, not right now. All right, how about its scale? There I am for scale, and with some crude CGI equivalent. Here's what LightSail would be in terms of dimensions when fully deployed compared to a roughly 1.8 meter tall human. So the program evolved to have two spacecraft, LightSail 1, whose goal was to develop and test the spacecraft functions and sail deployment, but not actually try to do solar sailing. So somewhat similar to NanoSail D2, but using our deployment methods and communication and such. Excuse me. It was launched May 20th, 2015 successfully. And when it launches in the configuration like this, except for it's about 45 minutes after launch that the small antenna pops out, which is shown down at the bottom. And so inside we've got, well, I'll talk about the avionics for LightSail 2 a little bit more, but let me mention that the kind of top 1U of the spacecraft is the avionics, it's the electronics, but also in there are, for LightSail 2, we have torque rods, which are basically electromagnets that we use to control its orientation relative to the Earth's magnetic field, can apply an electrical current, creating a magnetic field the way we want, and then it will push against the Earth's magnetic field and change the orientation. And then in one dimension, we have a momentum wheel, a spinning wheel that we spin up and slow down, and that does the bigger rotations of the spacecraft. After many days for both missions, we open up the 4 panels, and basically the outsides of the spacecraft everywhere, as well as the inside of the solar panels, are covered in solar cells to provide power for the spacecraft. There are 2 cameras, one looking in opposite directions. They're shown at the top of this image as one of them. And they're fisheye lenses, so they see 180 degrees and so create these somewhat distorted images. But that's so we can see most of both directions and see most of the sail. This is the dimensions of the spacecraft. It's the booms, the 4 booms that pull out the sail are made of an alloy called alloy. It's cobalt and chromium and some other good stuff. And those go out kind of like a tape measure, but the opposite direction. They're pushed out gradually, and the deployment takes about 2.5 to 3 minutes to get out to this 32 square meter sail area. And for reference, we have the loaf of bread. The fully deployed sail is roughly the size of a boxing ring, although boxing rings are not standard in size, but it gives you an idea. So here's the LightSail 1 launch, May 20th, 2015, on an Atlas rocket from Kennedy Space Center in Florida in the US. And here's the brief summary of the LightSail 1 mission. Sail did deploy successfully on June 7th. And then, as expected, because I failed to mention, it's hard to get launches into Earth orbit, particularly if you want to get free launches, or at least conceptually free. And so we went ahead and did this first launch knowing LightSail 1 would be in a low orbit, that once we deployed the sail, even though we think of that as space at 300 kilometers up, it's actually got enough particles up there that cause enough drag on the sail that as it pushes through the drag, it basically drops the spacecraft out of orbit within a couple weeks, and that's what happened. And so the overall result of LightSail 1 was success. We demonstrated what we wanted. Lots of things did not work right, and that was part of the point of LightSail 1. We learned a lot and made a lot of modifications to the spacecraft for LightSail 2. We were proud to win AIAA Small Satellite Mission of the Year, American Institute of Aeronautics and Astronautics. Now we move on to LightSail 2. And LightSail 2 had the grander goals of demonstrating controlled CubeSat solar sailing. How? By demonstrating a modification in orbit due to solar sailing. So this also would be an Earth orbit mission. for many reasons. Remember, we're a small organization in terms of application or implementation. And although this was a $7 million mission, this was a mission that would have cost 70 million US dollars or more if flown by NASA. So everything was done on a low budget, as carefully as we possibly could. And so part of what we did was we were able to get finally, after many delays, a launch into somewhat higher Earth orbit of the threshold we needed, which was around 700 kilometers, into a 720 kilometer near circular orbit on the launch of the Falcon Heavy spacecraft rocket from SpaceX. So we wanted to demonstrate in Earth orbit that you could actually do solar sailing, that we could turn the spacecraft, that we could control it, that we could change its orbit so it was different, not hugely different, but different. This is part of the key to spacecraft and trying to get them to work in space, as many of you are aware. Testing. And you can't test everything on the ground, and particularly for a solar sail, that big structure in a zero-G or microgravity environment, it's hard to test that, but you can test as much as you can. So we worked a lot. One of our partner universities is California Polytechnic University, San Luis Obispo in Central California, the coast. And they are actually one of the pioneers along with Stanford of CubeSats. And so they're a very logical partnership for us to have. This is doing one of our demonstrations of our tests of the communication, the deployment with just the panels deployed, and making sure that the communication and the antenna deployment, things like that worked. For those of you who might be familiar with him, our CEO, our Chief Executive Officer, is shown at the top here, is Bill Nye, the science guy, who at least in America is quite famous as a science educator, as well as an engineer. So here we did a LightSail 2 deployment test. So we did the best we could at testing the deployment on a horizontal table and having the booms slowly push the sail out. As usual, we learned things, we modified, we adapted. Let's see, hopefully this is a sped up video of about a 2.5, 3 minute deployment. Hopefully that came through the internet connection well enough you could get the idea anyway. And this was at Cal Poly San Luis Obispo, the university. This is an example of what the cameras on board the spacecraft, what they saw during the deployment. So that's the kind of view, minus the people, that's the kind of view we'll get in orbit, or we have gotten in orbit, and I'll show you later. One of the challenges with solar sails, and particularly when you decide, hey, we're going to fly it in a CubeSat, well, you got to figure out a really effective way to fold that sail to shove that 32 square meters into a spacecraft the size of a bread box. So then the spacecraft was integrated into what's called a P-pod, the Poly Picosat orbital deployer, which is designed by Cal Poly San Luis Obispo, has been used on many spacecraft CubeSat deployments. And it's basically a big, at least what we'd call a jack in the box. There's a big spring inside this box. You shove the spacecraft down in against the spring, you close the door, and when you're in space, you open the door and it pops out. But in order to get the launch, we actually were launched inside a Georgia Institute of Technology, US University, their spacecraft called Prox-1, where we were launched inside that. And then 1 week after they were in orbit, a timer went off and we got deployed with the spring. And it was part of a US Air Force technology payload where they did a competition for universities to get a launch, and they got a launch. And so we partnered with them and were launched inside it. Here I am looking all clean room decorated and ready for the tests of the integrated spacecraft. Then it moved off to Florida for integration along with 23 other spacecraft into the Falcon Heavy. Here you can see the outline shows our spacecraft where it would be inside the Prox-1 spacecraft attached to the deployment ring, one of the rings on the inside of the Falcon Heavy. And by golly, after multiple years of delays of the Falcon Heavy launch, we launched on June 25th, 2019. And it was did just what it was supposed to. There's a picture of some of our members attended the launch, getting very, very excited. So we had nothing. We had no communication as planned, nothing from our spacecraft. It remained off inside Prox-1 until 1 week after launch. And then, as I mentioned, the antenna deployment, and I discussed this, so I'll skip ahead. Here's a sequence from left to right of us waiting in the control room for a signal from the spacecraft. Happy people when we get a signal from the spacecraft. And in the lower right is a waterfall plot that shows the Morse code that the spacecraft broadcasts every 45 seconds in a continuous wave that identifies the spacecraft, which is particularly helpful when several CubeSats were deployed at the same time to identify which one is ours and to confirm that it was ours. The spacecraft also, as we'll discuss, sends out beacons, basically engineering telemetry data every 7 seconds, and that's what tells us the health of the spacecraft. Tested out the cameras while they were still inside the box and before deploying the solar panels, and there was enough sunlight leakage through the edges of the box to see the bottom of the motor mechanism. And then we went, after confirming everything was healthy enough, we deployed the solar panels, which freed up the cameras, and then got pictures of Earth. Yay! And so here's one of our few pictures we got before solar sail deployment. And here's engineering at work. Shoestring budget creative engineers. That's Dave Spencer, who is our project manager on the right, and Alex Diaz, one of our engineers on the project from Ecliptic Enterprises. Dave was at Purdue University at the time. He's now at JPL, NASA JPL, as one of the lead people for a Mars sample return, but is still doing our project management on the side while we're in orbit. And we have sun sensors that were not behaving the way we expected. So here they've set up their cell phones, flashlights over BenchSat, which is a flat sat. It has all the parts of the spacecraft in working order, most of the parts, but not looking like a spacecraft for testing. And they were testing various angles and such of the sun sensors to figure out how to troubleshoot an issue. Sail deployment, really the tense time of the mission. We talked about the sail here. Let me go back. So this may be tricky to see. What I'm going to show you are thumbnail images, so very tiny images. For each picture we took, we designed it so theoretically, at least, we get a thumbnail which is only 120 by 90 pixels. So we can send those back to Earth because we have pretty low data transfer to Earth, and then choose what pictures to downlink at higher resolution. So first I'm going to show you the movies we made from the 2 cameras from sail deployment, where they get out of sync because they have a different number of pictures, but you'll see them kind of in sync to begin with. And so you can see our sails deployed, and there was much rejoicing, much happiness. And let's look at a high res. This is during the deployment. This is over Baja California and Mexico. And you can see the boom in the middle there. The booms before the sail covered them up. The booms deployed. Nice shiny sail. Notice other than the folds, there are not many wrinkles, not many so-called crinkles. And it looks good. And this is the opposite direction, looking out with the sun coming through the sails shortly before the end of sail deployment. There is, you will see in some of the images, and in the lower left here, there is a fishing line-like material called spectraline that was holding the spring-loaded solar panels together. And when it was a burn that breaks those fishing line pieces, and that allows the spring-loaded pieces to come up. Well, it didn't get completely out of the way. So on one of our cameras, you will see this fishing line type stuff periodically. So here's another look more slowly at 5 images from each within the deployment. And the pictures get spaced farther apart later on because of the time needed to compress the images to fit them in our memory. But you can get an idea of what it looked like. All right, how do we sail? Well, first of all, I'll make a comment that what you want to do with solar sailing is use it between the planets. What we did, because it was the way we could build a system that we could do and test everything out, was do it in Earth orbit. But kind of like sailing a sailboat in the harbor compared to sailing a sailboat in the open ocean, in that respect, it's actually harder to do it in Earth orbit, because on the open ocean, you can pretty much set your sail and go, and maybe tack occasionally. In the harbor, you have to keep turning back and forth. And that's what we did to show that we could adjust the orbit. We would slew or turn over about 2 or 3 minutes. We'd have these 90-degree rotations of the sail between on and off attitude. So if you picture in this diagram, the sun coming from the bottom, when we were headed towards the sun on the left, we would try to be edge on. That's what at least we would attempt to do, and then rotate the sail at the subsolar point, and then you have a push from the sun on one side of the orbit, and then go edge on again. So it's pushing one side of the orbit and not the other side, which will tend to increase the orbital energy if there were no effective drag, which there was, but still it will make an effect on the orbit that we can measure. So it is an important point that ideally we would have launched to an even higher orbit, but you take what you can get, or been in deep space. Even at 720 kilometers, when you have a 5-kilogram spacecraft and a 32 square meter sail, there is still enough drag from what little atmosphere there is up there that it will drag your spacecraft down. And so occasionally we actually increase the orbital energy, or pushed out the orbit, but usually it was a matter of trying to demonstrate that our orbit decreased less than it would have if we weren't sailing. And we did demonstrate that, as I'll show you briefly. And this was to demonstrate that we had active solar control. So we have an attitude determination and control system, ADCS, which takes inputs from magnetometers that tie to Earth's magnetic field, from solar sensors that identify the approximate direction of the sun, from gyros, which give us information about the spin rate, the rotation around 3 axes, and all of that is chewed on and determine what continual adjustments need to be made to sail orientation to try to look as much like that perfect control system I showed you on the previous slide. And so what the data is showing down here is time is along the horizontal axis. This was from very early in the mission. So we were trying to convince ourselves that we were getting the sailing at least sort of right. And this is the -z in our spacecraft being pointed to the sun. So ideally, our spacecraft over time would have followed this red line. So where it's pointed at the sun for half an orbit and pointed 90 degrees to the sun and the other half of the orbit. And you can see we didn't make it perfectly, but we got pretty close considering our system. Our system only has a capability of assessing the orientation to within 15 degrees, maybe 20 degrees. So again, because of what we could use in terms of sensors, we're somewhat limited, but this Shoto is doing what we wanted it to be doing. This is one of the key things early in the mission, and we have a lot more data since then, but this demonstrates what I want to show you, which is how do we determine that we really are making a difference with solar sailing? After all, most of the time, our orbit is continuing to decrease because of the drag. Well, this shows you in blue, well, I'm sorry, the horizontal axis is the rate of change in the semi-major axis. So on the average orbit, you can think of it's shrinking the orbit by how much each day and in meters. And then it's a histogram with number of times that you are doing it in that amount. I didn't say that very well, but the point is blue, when we're solar sailing, the orbit decreased less, it even increased occasionally, more often, whereas when we weren't solar sailing, when we were in an uncontrolled mode, we have various modes in the spacecraft, it tended to be greater loss, and that continued to be what we have seen throughout the mission. So I won't skip through a lot of this, but basically we proved once again for the millionth time in spacecraft exploration, hey, it can help to have a camera when you want to assess what's gone wrong or when you want to learn what's happening. So I and others noticed in this image on the lower right, we have shadows of the solar panels on here, but the one panel is on the lower part, the lower left, looks kind of flopped over. And indeed, one of our panels, 4 panels, instead of deploying up like this to like 155 degrees, deployed to like 90 degrees. And so that was causing our magnetometer readings, which we have on multiple panels, to be totally in disagreement. And this is what allowed us to realize what was going on, did some analyses, made adjustments so that everything adapted to that situation, and it no longer is really a problem for us. Also, the boom is in an unexpected location. One of the booms buckled on deployment, and we see it extending outwards somewhat over the mission. We also see things in the sail. So as we look at images later on, I'll point out, whereas we had that nice smooth sail initially, now there's a lot more wrinkles. There are places that seem to have delamination. In other words, the aluminized part has come loose from the mylar, the material underneath. And this is likely caused by, it turns out, well, it's probably poor phrasing, in that part of the upper atmosphere, atomic oxygen gets to play. It doesn't, there aren't enough molecules that atomic oxygen doesn't join with oxygen and form neutral oxygen. It can exist on its own, and atomic oxygen tends to beat things up and cause degradation of things like mylar sails. So we're watching that over time to learn more about that. All right, how do we do on our goals? We demonstrated controlled solar sail, CubeSat solar sail propulsion. We raised the public and technical profile of solar sailing. We definitely excited and engaged the public, and we are in the process of sharing our results. So we're pretty happy with the LightSail 2 first small spacecraft propelled by sunlight alone, demonstrating the viability for using this type of thing for deep space probes. First crowdfunded, so funded just by people, not governments, spacecraft to test a new method of propulsion. First controlled solar sailing flight in Earth orbit, and highest performing acceleration solar sail to date. So that's that area to mass ratio that basically, because we have a much smaller spacecraft than say Icaros, even though we have a smaller sail, the ratio is 10 times higher acceleration for LightSail 2. And then I'll show things we're kind of proud of, that at least the press noticed us. And so Time magazine in the US put us on the 100 best inventions 2019, Popular Science, most impressive aerospace innovations 2019. And if any of you watch a Jeopardy game show, there actually was a reference to our spacecraft on one of the questions. Here's our team over time. This has been a program that's been going since 2009. And so we've had a number of different organizations involved, which hopefully you can read on your screen there. A lot of involvement over time and changes, and it's been quite a roller coaster. This is the current operations team. This is the people we meet almost every day by phone and figure out the next plans. Dave Spencer, I mentioned. John Bellardo at Cal Poly San Luis Obispo is the head of our communications for the spacecraft and software, and the person who actually used the open source OpenMCT that you'll be hearing much more about than I can tell you, and adapted it to our mission. Barbara Plant from Boreal Space, ADCS, and Justin Mansell, who got his PhD partly using LS LightSail 2 from Purdue and is now a researcher at Purdue. So in the extended mission that we're in now, we're trying to improve our solar cell performance, operate in different modes, see the results, continue to take pictures to inspire people. We have Justin Mansell created a ground-based fault protection algorithm that he's been testing out on our system to find out what's going wrong at any given time. Share the mission. There are 3 upcoming NASA solar sail missions, and we've been coordinating with them and sharing what we've learned. NeoScout is scheduled to launch sometime soon, theoretically, on the first launch of the Space Launch System SLS rocket. And then ACS-3 is a Earth orbiting mission out of NASA as well. And then they've recently selected Solar Cruiser, which is supposed to go out to that L1 Lagrange point to prove that you can do it. And then we're documenting things and carrying out maintenance, etc. Tying a little bit to this workshop, which this is a partial example of a beacon that's been converted to format that humans can read. So we have 334 lines, different data points that get transmitted every 7 seconds from the spacecraft that we pick up when it's passing over one of our ground stations. And it's also more telemetry stored on board. And this is kind of what we look at if we want to learn something. But OpenMCT, which you'll see is far more capable than what I'm going to demonstrate, but just to show, we do use it for all sorts of things. I look at it pretty much daily to figure out the status of the spacecraft. This is a plot showing time on the horizontal axis and our different modes that we go into. So solar sailing, detumble, which that momentum wheel saturates periodically. If you keep using it to turn, eventually it reaches its limit. And so we go into a mode where we use the magneto-torquers to desaturate it. And that's what's shown with the detumble. And then we put it briefly into a no torques mode where it just kind of rests. And then we go back into that solar sailing mode. And this shows what you kind of don't want to see, but tells us a lot, which is the long duration counter. So this is basically showing us reboots over plotted like a month of data. And so there are times when we have issues with multiple reboots periodically. And so this allows us to quickly assess that. And then the data free in our that we can use for images and telemetry is shown in the other graph. So really my point is we use it a lot. We're very appreciative that it exists. We use it far more in more detail than what I've shown, and John Bellardo is really our expert on that. Let me just finish with some pretty images, which is kind of my part of, I'm the program manager, but I'm also kind of the imaging guy, scheduling images and pictures and processing them. So around the equatorial world in pictures, we're in a 24-degree inclination orbit. So we have trouble seeing not trouble. We just don't see the farther latitudes, higher latitudes, north and south. This is a picture of the Bahamas and the eastern coast of the United States. Always pretty water of the Bahamas. The west coast of India, north is at the right. The sun can be seen poking through the sail, or shining through the sail in the middle. This is Eastern Australia. North is at the left. And this is one that had shadows on the sail. The first was like, wait, that's not right. So I did some very complicated engineering analyses using a tiny model and a flashlight to recreate the pattern of the panels and show that, yeah, if you put a panel around 90 degrees angle, that would cause it. And then we used magnetometer data to confirm and come up with a better, more accurate analysis than me at my dining room table. This is something which shows that the sail over time, due to probably the wrinkles and crinkles, it's the softening of the mylar in the atomic oxygen environment, is gradually coming inwards. So you see the dots mark where it was, but basically as it gets wrinklier and it comes inwards, this is the other sail. Sorry, I'm going fast, but I know I'm running out of time. So that's the main point. Here's the southwest coast of Australia. North's at the lower right. Caribbean, the eastern tip of, you got Cuba and Hispaniola. And this is Western Africa. Mali, Niger River is what you see in the, as that black snaky looking thing on the left side. One of my favorite pictures, the Himalayas in Tibet. North is roughly at the top. India is at the left. And that's the Himalayan Tibetan plateau. Typhoon Vamco in the Philippines, which you can see if you look carefully in the mid right, and beautiful pattern of a typhoon. And Northwest India is with north at the left. The Andes, so you can see Chile on the left and Argentina and Brazil on the right, and both the Pacific Ocean and the Atlantic Ocean. And you may say, hey, where's our picture of Turkey? Did you get Izmir? Well, it's really hard to get your latitude. And you can see if you look very carefully at the upper right, I got southern Turkey. I got the spacecraft. There was a partnership of lots of people, obtained an image of southern Turkey, didn't quite make Izmir, but we did a beautiful shot of the Red Sea and the Nile River and Nile River Delta and the Eastern Mediterranean. And we will, for more information, you can always go to sail.planetary.org. And from there, there's a link to our mission control that shows where the spacecraft is and some basic telemetry and orbital information. Yeah, and I'll leave it at that. My email is at the bottom, and I'll turn it back over to the organizers for what happens next. Sorry if I went a little bit long.
No, Bruce, this was fantastic. Thank you. Very inspiring. And this is precisely so much to say. Lovely, really great. And I wanted to say, you may not know this, but Jason Davis will tell you that you may not have seen Izmir, but Izmir saw LightSail too.
Yes, I'm aware of that.
Yeah, so it was and for those of you who don't know, Jason Davis at the Planetary Society declared that I was the first to see this spacecraft from the ground, actually. And it was very low on the horizon, which probably explains, you know, the reason that you didn't see us. But it was a fantastic mission, really. I have this question concerning the plots in which you show the, you know, the orientation as square waves and the reality of that. I don't know what you would call those diagrams, technically speaking, but anyway, if it is a sense, yeah. So my question is, from the engineering standpoint, was that the torque applied to the spacecraft was not sufficient? Or, I mean, if you could improve something from the engineering standpoint to make that compliance better, what would you do?
I would, a number of things, but probably the first thing is get better sensors. So it was, I think as much as anything, it was an issue with our attitude knowledge as much as our attitude control, or more was the attitude knowledge, which was based on sun sensors, which were honestly designed for like automobiles and weren't spacecraft level sensors. And our magnetometers, which were also helpful. Having a higher quality magnetometers would have been helpful as well. So we had an inherent measurement issue of like 15 or 20 degrees at best. And so then the spacecraft, the ADCS software is constantly trying to adjust, and so is overcompensating or undercompensating or not getting it right. I mean, there are a lot of other things to improve as well, certainly, but that's where I'd start. And
one other question before I let you go. At the level of theory of solar sails, imagine, because my students, explore these spacecraft parametrically.
Right.
If you were to take a spacecraft that has the same mass as far as the CubeSat itself, but you wanted to make an area that is 100 times more, hypothetically. So you increase the size to 10 by 10 than what it was. How much would the mass increase?
I used to know the mass per square meter, but I really don't remember it. I mean, before you ever got there, your challenge would be shoving that into a little tiny space.
Yeah. Of course.
I don't know. I'm sorry. I could guess, but I might guess wrong. I could follow up with an email to you about based on our mass per area.
That would always be appreciated. So anyway, I would like to thank you on behalf of all of us. I know how busy you are, and please understand that we know it's an honor to have a mission manager that comes over to tell us about a space mission that was successful. And really, we deeply appreciate it. And I want you to know that my students study LightSail 2 as a matter of assignment during spacecraft design and other classes. We take it very seriously. I mean, it's
that's great. It makes me feel good, and I'll let our team know that as well.
Please, that will be great. We wish you the best. And Bill Nye, the science guy, has always been. I raised 2 daughters in Pasadena, and we were I had one daughter that went to Westridge, and so it's very it's home to me. Let's put it this way. So
yeah.
Thank you very much. Yeah, I know.
All right, take care, everyone. Thank you very much. It's an honor to have been asked to participate, and you're doing great stuff there.
Thank you so much, and please tell the team, and yourself, you're welcome in Izmir, please.
Thank you very much.
Thank you.
Take care. Bye-bye.
Bye-bye.